Um, do you mean to be muted?
Oh, I did not mean to be muted. Okay, great. So just to uh, just to go back, so today we're going to talk about something known as Gordon's escape through the mesh theorem and applications of it to dimensionality reduction, like JL. Um, so there are three places where we've seen Euclidean dimensionality reduction so far in the course. One is the JL lemma. So you're given, actually I'll just say this: you're given X, which is a subset of, let's say, RD that's finite, and you want that for all x, y, little x and little y in capital X, the norm of pi x minus y, or actually, let me write it like this: the distance after you apply pi between x and y, the square distance is roughly like what it used to be. In other words, if you define t, which is the set of all vectors x minus y normalized by the norm, what you want is that the maximum of, let's say, z and t of pi z also norm squared minus 1 z plus epsilon. Or like that's right. That's what you want in JL. And here pi is m by n or m by d, and you can get m to be at most up to a constant 1 over epsilon squared times log of I guess here log n. Okay. So which is basically 1 over epsilon squared log the size of t. So that's JL. Now, if you look at subspace embeddings, you all had a PSET due recently, PSET 2, where basically what you want is, so E is a let's say d-dimensional um, subspace of Rn. So you can think that T now is basically E intersected with the unit ball of radius 1. And then what can you get away with? On the p-set, you should get away with d over epsilon squared. You did that by basically applying JL to a net of the subspace, of the unit ball of the subspace. And then there was also another part of that p-set problem for RIP matrices, where now T is basically the set of all k sparse vectors intersected with the unit ball of the unit ball there, and then there you got that m was at most something like k times log of en over k over epsilon squared. Right. So these last two examples, they don't. I mean, they do follow from JL after you apply a net argument, but they're not just immediate applications of JL, right? Because these t's are not finite. So log t would be infinite, which wouldn't make sense. You have to say more. Um, so what I'm going to show you today is a general theorem that applies all three of these kind of uh, automatically, and more. Okay. So the general theorem is due to Gordon in 1988. Is say that pi is an m by n matrix, and the entries are IID, normal, mean 0, variance 1 over m. So basically just take standard Gaussians and divide the matrix by root m. Then for all t of subset of the sphere, so now t is, everything in t has unit norm. This will be true an expectation over pi, the sup over x and t of pi x squared minus 1 with the utmost epsilon, as long as the number of rows of pi is at least some constant times the Gaussian mean width of t squared over epsilon squared. Okay, so that's the theorem. If you haven't seen this before, you might. Well, actually, let me know just to be less confusing. I'll use a different letter. I'll call this W, where WT is the so-called Gaussian mean width of T. So what does that mean exactly? The definition of it is you take a vector G of IID standard normal random variables, mean 0, variance 1, and you look at the maximum over all x and t of G dot x. And the expectation of that maximum is the definition of the Gaussian mean width. Okay. So I'll show you quickly why this is stronger than all the previous three things. This implies JL automatically. It implies subspace embeddings with d over epsilon squared rows. It implies RIP matrices with the right number of rows. And then once I show you that, and maybe I'll show you another example of kind of controlling this Gaussian mean width, then we're going to move on to like, how do you prove Gordon's theorem? And actually, Gordon had a proof that was specifically for Gaussians. It didn't work for other distributions. Now what we know is that this theorem holds even if the entries of pi are sub-Gaussian, meaning they decay at least as fast as the Gaussian. So for example, plus minus ones would work. Rademacher's would work. And today what I'm going to do is I'm going to show you how to prove Gordon's theorem for Rademacher's. That's going to be implied by something called the majorizing measures theorem, which is a bit more complicated that I'm not going to be able to prove today. But then given that majorizing measures theorem, I'll show an argument from 2014 by Kramer, Mendelssohn, and Rahut on getting the theorem from that. Okay, so before we move forward, are there any questions about the statement of anything I've said so far?
Yeah, sorry, what is S?
Where did I write? Oh, I just mean the unit sphere. So Sn minus 1 is the set of all vectors in dimension n that have Euclidean norm exactly 1.
Okay, I see.
Right. So if you look back at, I mean, here I could have actually, all these things, I could have, so I should have said n, Sn minus 1, Sn minus 1. Right, so, right, because as long as pi preserves everything on the sphere, it preserves everything off the sphere as well because it's linear. Okay, good. So now I want to show you, like, okay, so we have a bound in terms of this weird quantity WT. Like, how do you even understand what WT is? Like, if I give you a T, how do you know what WT is so that you could actually apply this theorem? And in particular, how do you do it to imply these three bounds that are boxed on this whiteboard over here? Okay, so let me show you. So next.
Actually, what's the distribution on G in that expectation? Is it
So
Gaussian?
G is distributed like a normal random variable. It's a vector.
Yeah.
Its mean is 0, and the covariance matrix is identity. So in other words, like G is an n-dimensional vector where each GI is independent and mean 0, variance 1, Gaussian.
Yeah.
So next, how do you bound?
I have a question.
Yes.
So should the entries be like normal with variance 1 over n? Because wouldn't that lead to like isotropic like rows? I think.
No. I mean,
no. Okay.
so this, sorry, just to be clear, this G right here is
Oh,
not.
for pi.
Oh, yeah, I did divide by M.
Oh, it looks like M. Sorry.
That's an M. M like Mary.
Oh, but shouldn't it be n so that the rows are like isotropic? Like
Well, there are M rows, right? So I mean, just think about it like this: pretend pi only had one row. Pretend pi was a
uh-huh.
vector. And now you look at the x. So like, let's call the row the single row of pi is G, a Gaussian vector, and look at G dot x, and look at the expectation of G dot x squared, right? Like the expectation of G dot x squared. This is basically pi x L2 norm squared, if it's just one row. This is equal to the expectation of the sum of Gi xi.
Would a row vector correspond to m being 1?
Yes, exactly.
Oh,
I'm just trying to
okay.
convince you that you
Oh,
shouldn't
okay.
divide by n. You should divide by m.
I see.
Yeah, because just taking the dot product of the single row and squaring it gives you the correct expectation. So if you have m rows and you're adding them up,
I
then
see.
you need to divide by m to get the expectation right. Does that make sense? Yeah. Okay.
Yeah. Okay. Thank you.
No problem. So next up, how do you bound this Gaussian mean width anyway? So how to bound the Gaussian mean width. So it turns out that there's an optimal answer that's known as generic chaining. I'll say what it is, but I'm going to work our way up there. So the easiest way is the union bound. Okay. So remember now, G dot x is the sum of Gi xi, and the Gi's are independent. So you're summing up a bunch of Gaussians. Each Gaussian has variance xi squared. So what's the variance of the sum? It's the sum of the variances, which is the sum of xi squared, which is 1, because all the xi's are on the sphere. So each one of these G dot x's is a Gaussian. And you have t Gaussians, or t, let's say t is the size of t. Sorry for overloading variable names. Right? So if you have t Gaussians and you take a union bound, it's probably not bigger than root log t. So kind of trivially, the Gaussian mean width is always at most root log t. So let me write that down. So W of t is equal to the expectation over G of the sup over x and t of G dot x, which is equal to the integral. Well, let's say that's at most putting the absolute value there, which is equal to the integral from 0 to infinity of the probability that the sup of G dot x, probably over G, sup over x, in t, is bigger than lambda d lambda. Actually, let me not call it lambda, u du. Okay. And then I'll just break up the integral into two parts. This is the integral from 0 to lambda of that probability, plus the integral from lambda to infinity of that probability, is du. And I'll choose lambda to optimize this calculation, but probabilities are always at most 1. So this is at most lambda. And for this part, I'll just use the union bound. So this is at most the integral from 0 to infinity of the sum over all x and t of the probability that G dot x is bigger than u du. So this is the union bound. I did a union bound over all x. This I can just use Gaussian decay. This is what we said. G dot x is a Gaussian. It's a Gaussian with variance 1. What's the probability that a Gaussian is bigger than u? It's like e to the minus u squared. So this is at most, this is just a property of the tail bound of Gaussians, 2e to the minus u squared over 2 or something. Okay. So this is at most now the integral from 0 to infinity of the size of t, because I sum over all x and t, 2e to the minus u squared over 2 du.
Should it be an integral from lambda to infinity?
Yes. Okay. And this is going to be some like t times e, so 2t times e to some minus theta of like lambda squared. Okay. So now overall, putting everything together, we have that it's at most lambda plus t times e to the minus theta lambda squared. So now what I'll do is I'll optimize by choosing lambda to be some up to a constant, basically square root log the size of t. And then if you do that, you'll get here, this is at most square root log the size of t. Okay, so this is just always true. The Gaussian mean width is always at most root log the size of t. I mean, assuming t is a subset of the sphere. Okay. So you plug that into this bound. What do you get? Root log t squared, which is log t, over epsilon squared. That's exactly JL. Okay. So already just kind of trivially bounding WT via the union bound gives you JL. Well, I mean, once you have Gordon's theorem. And you know, I should say, like, you know, this root log t can actually happen if, for example, you know, when is this tight? It's basically tight when the GIs actually, when the different Gaussians are actually independent. Okay. When are they independent? They're independent if the x's are orthogonal. So, for example, if your set of vectors is the standard basis vectors, okay, then the mean width will be theta root log t. When is root log t not tight? It's not tight when the vectors are not orthogonal, and or you know, more specifically, if you really want to make it small, like the extreme case is that all the vectors are the same. If all the xi's are the same, then of course a union bound is wasteful, because if one random variable is small, they're all small because they're the same. So the thing to keep in mind is, okay, so they're not exactly the same, but like, let's say all the vectors in T are really, really close to each other. They're like, you know, they're clustered in a very, very small region. Then again, the Gaussian mean width will be small. Okay. So what's one way to bound the Gaussian mean width by something small when it is small? Let's say when the points are really well clustered. Well, technique number 2 is what I'll call using an epsilon net. Okay. So we know what epsilon nets are. Why are they useful here? Say T prime is an epsilon net of T under L2, and like I'll use the notation that like x prime is the closest thing in the net. So for all x and t, there is an x prime and t prime, such that the distance between x and x prime is at most epsilon. Now what? So Wt is equal to the expectation over g, the sup of g dot x. But I can write x as x prime plus x minus x prime. So this is equal to expectation over g, sup over x and t, of g dot x prime plus x minus x prime, which is at most the expectation over g, the sup x and t of g dot x prime plus the expectation over g sup x and t of g dot x minus x prime. Okay. Now, what is this? This, by the last slide, is at most the square root log of the size of t prime. And the point is, even if t is big, if it has a very small net because the points are very closely clustered together, then I only have to pay root log the size of the net, not root log the number of points. And then here, what do I do? This is certainly by Cauchy-Schwarz at most the norm of x minus x prime, which is epsilon, times the norm of g. But the expectation of the norm of a Gaussian vector is root n. So this is at most, you know, so let's say expectation over g, so this is at most epsilon root n. So altogether, this is at most root log. If you remember this notation, if not, I'll remind you. So T L2 epsilon plus epsilon. Right, so remember capital N is called the covering number or the entropy number. What this means is, what's the smallest size of an epsilon net of T under L2? And what's epsilon? Well, epsilon could be anything. We can choose epsilon to optimize this. So this is at most kind of the inf over all epsilon. We can choose epsilon to minimize this expression. So for example, we could choose epsilon to be 0. If we choose epsilon to be 0, we're saying that our net has to be T itself. And then you're just reducing to the previous whiteboard, right? You're just going to get root log the size of T. But you're allowed to choose any epsilon in between as well. Okay. So that's and sometimes this gives you something better. You can take it one step further, and you could do Dudley's so-called Dudley's inequality. Okay. What is this? I'll call it. I want a good letter. QS be a 1 over 2 to the S net of T under L2. Okay. Without loss of generality, T is finite. Okay. Why is that without loss of generality? Because what I can do is I can write so if I just go back one slide to the epsilon net argument. So I know that, I'm only considering T's, which are subsets of the sphere. And the sphere itself has a bounded size net, right? We know that the sphere itself has an epsilon net of size at most 1 over epsilon to the dimension. Okay. So what I could always do is I could just apply argument 2. Okay. I could apply argument 2 to a very, very tiny epsilon, like as small an epsilon as I want, so that this thing basically goes to 0. And then what I could do is I can now apply whatever argument I was thinking to apply to this. Right. Kind of what you can think of the epsilon net argument as saying is, without loss of generality, I can always assume that I'm trying to bound the mean width of a finite set. Here I bounded the mean width of the finite set T prime by using the union bound, but nothing forced me to use the union bound. I just basically reduced to another mean width problem, right? This is the mean width of T prime. So whatever more sophisticated tools I have for bounding mean width, I could use those tools to bound mean width of T prime. So that's what I mean when I say without loss of generality. Pretend that T actually is T prime. We already approximated it by a super, super fine net. And then now we're just focused on a finite thing. And I'm going to say let xs be the closest point in QS to T. Now observe, I can write x as being x0 plus the sum s goes from 1 to infinity of xs minus xs minus 1. Does that make sense? Why? Because let's just think about this. So let's imagine expanding that sum just one summand at a time. So initially the right-hand side is just x0. Once we add in the first summand, it's x0 plus x1 minus x0, so it becomes x1. Then we add in the next summand, we add x2 minus x1, the x1 cancels, now we have x2. So every time we add another summand, we basically are we're getting kind of the next level of refinement for x in the next net. So it's going to be x3, then it's going to be x4, then it's going to be x5. And basically that's because t is finite, at some point qs is just t, right? Like once 1 over 2 to the s is smaller than the smallest intra-set distance, we're basically just forced to set qs to be t. So at some point, like, there is an s star such that once s is at least s star, xs has to equal x. In other words, even though I wrote this as an infinite sum, it's really a finite sum, because beyond a certain point, all these differences are actually 0.
So each x like gets its own xs.
So I say it one more time.
Like each point x gets its own x0, x1 up to.
Yeah, well, yeah, x0, x1, x2, etc. is like a sequence of points that more closely they converge to x, and they more and more closely approximate x, because xs comes from a 1 over 2 to the s net. So the distance from x to xs is at most 1 over 2 to the s. There might be different x's that share the same xs, right? I mean, the original x is very huge. xs is some smaller set. It's a net. Okay. But so this just makes, yeah, go ahead.
Yeah, I should say let xs be the closest point in qs to x instead of to t.
Let x be the closest point in qs to x. Yeah, I should have said that. Good point. Yeah. Okay. So this implies that g dot x is equal to like g dot x0 plus the sum of g dot xs minus xs minus 1. Right? So this implies that the expectation, basically, just remember what is the mean with mean, wt, which is equal to the expectation over g of the sup of g dot x, is equal to, I'll just do the sup separately. It's at most the expectation over g of the sup of g dot x0 plus the sum, s goes from 1 to infinity, of the expectation over g of the sup x and t of g dot xs minus xs minus 1. Okay, so whatever our point is, whatever our set t is, like, it's contained in the sphere. So for q0 has to be a 1 over 2 to the 0 net, so it's a 1 net. So we could just set q0 to be the point 0. The point 0 is always within 1 of everything. So that means there's really no sup here, because there's only a single x0, which is 0. So this basically, I'm just saying that this whole thing, this whole thing is just 0. Okay. Now, if you look at this, what can I tell you about that? Well, xs minus xs minus 1 by triangle inequality is equal to, well, first of all, it's equal to xs minus x plus x minus xs minus 1. I just added and subtracted x, and then by triangle inequality, this is at most the distance from x to xs plus the distance from x to xs minus 1, which is at most 3 times 1 over 2 to the s minus 1. In fact, let me just write it as 6 times 1 over 2 to the s. So it's big O of 1 over 2 to the s. So, right, we talked about this. Like, if you have a set of unit norm vectors and you look at the mean width, you get at most square root log the number of vectors. But now the vectors are not unit norm. They're of norm at most 6 over 2 to the s. So let's say they're norm at most, they're all, instead of norm at most 1, they're all norm at most alpha. So you could just apply the previous reasoning. You could, for example, just normalize all the vectors by alpha. Now they do have at most unit norm. Okay. And then you get root log the number of vectors and then put the alpha back. So all I'm trying to say is that this thing now is at most kind of the max norm of anything in there, which is 1 over 2 to the s, 6 over 2 to the s, times square root log. How many vectors are there of the form xs minus xs minus 1? Well, the number of such vectors is at most the size of qs times the size of qs minus 1. qs is a finer net than qs minus 1, so qs is bigger. So this is at most the size of qs squared. But like log of the square and log without the square are the same thing up to a factor of 2. So I can pretend the square is not there. So this is at most basically log 1/2 the size of qs over 2 to the s, which is, log to the 1/2 of the covering number of TL2 1 over 2 to the s divided by 2 to the s. So all in all, what we've seen here is that it implies that the mean width of t is at most the sum s goes from 1 to infinity of 1 over 2 to the s times square root log the covering number of t with respect to L2 with radius 1 over 2 to the s. This, by the way, is called Dudley's inequality. Oftentimes when people write Dudley's inequality, like in it's a very like well-known theorem. You can find it in textbooks. Oftentimes when people write it in textbooks, they just approximate this sum by an integral. Like the usual trick of, how should I say it? So you can think that you're plotting something where you whatever, so root log, remember, I don't know whether it's increasing or decreasing, but there's the usual trick when if you have a set of curves like this and you're looking at this area, you can just like bound that by like the area under this curve. So you can do the same kind of reasoning here and say that actually this thing up to a constant is at most the integral of square root log covering number TL2u du, integral from 0 to infinity. So u is basically like the 1 over 2 to the s. Okay. Writing it as an integral or as a sum, it doesn't really matter. Okay. I'm just letting you know that if you Google Dudley's inequality, you will most likely see it in the integral form, but it's the same as writing a sum. Okay, so this Dudley's inequality is already good enough that you usually get like pretty decent results using it. There's one more level of sophistication called generic chaining. You can come up with examples. Where Dudley's inequality actually gives you the wrong answer. But there's a theorem that says that whatever answer you get from Dudley's inequality can only be off from the truth by at most a log dimension factor. So here we're in dimension n, let's say. So it'll at most overestimate the mean width by a log n factor. And an example where that happens is if you set t to be the L1 ball. Okay. So imagine you looked at actually the expectation over g of the soup over x in the L1 ball of radius 1 g dot x. So even forgetting randomness, what is this? What is the sup over x in the L1 ball of g dot x?
The norm of G.
Which norm?
With the L1.
It's the L
No.
infinity norm.
Infinity, no, yeah.
Yeah, so the L infinity and L1 are dual norms. If you're trying to maximize this, what you should do, you should think that like since the sum of the xi's have to be 1, or I mean the sum of the absolute values of the xi's have to be 1. You can think that like what this is doing is it's averaging the entries of G. Right? It's doing a weighted average of the entries of G, where the weights are the xi's. And you're allowed to choose the weights to maximize the weighted average, right? So if you're trying to maximize the weighted average and you can choose the weights, what should you do? You should put all the weight on the largest coordinate of G. So whatever the largest entry of G is, you make that xi either be +1 or -1, whatever it needs to be to, basically it should agree with the sign so that you get something positive when you take the product. So then the sup will be the L infinity norm of G. Okay, so G, remember, is an n-dimensional Gaussian. Each entry is like an independent Gaussian. So you have n Gaussians. You're taking the L infinity norm, so that's the maximum of n Gaussians. So like, what do you expect? What should the expectation be? Right. What's the expectation of the maximum of n Gaussians, of n independent Gaussians? We did it already. Right?
Square root log n.
Yeah, square root log n, right? So we already know what the right answer should be. The right answer should be root log n. And if you do Dudley's inequality on this, and you try to integrate square root log of the covering number, it's not completely trivial to figure out what the right covering number is, but it's doable. And I promise you that if you do it, you're going to get log to the 1.5n. So you're going to be off by exactly a log n factor. And and the reason is because Dudley's inequality itself is suboptimal. Okay. So there is one more level of sophistication that always gives you the right answer, no matter what t is. And
I have a question.
Yeah, go ahead.
What if we packed with L1 balls instead? Is it because of the L1, like we're using L2 balls in Dudley's?
Oh, like why are you getting the wrong answer?
Yeah, like if we, yeah.
I don't have a good. Well, here's the interesting thing. I mean, what I can tell you right now is like I'll show you what the next level of sophistication is. The next level of sophistication still is like it's still only ever talking about L2, but somehow it's just a little more. It's a little fancier.
Okay, thanks.
So let me just write down what that next level of sophistication is. And this is due to Fernique. And then in its current form that I'm going to discuss, it was described by Talleyrand. Okay, so here, let's rewrite Dudley. Okay, so let me give a definition. You say the sequence TR, R goes from 0 to infinity, is an admissible sequence if for all R, TR is a subset of T. Or actually, let me just write it like this. T0 is a subset of T1, is a subset of T2, is a subset of T. And also T0 has size 1, and TR has size at most 2 to the 2 of the R for all R. And so we're going to look at all sequences of sets that look like this. I claim that the mean width of T, let me write it like this. I claim that Dudley implies, or it's equivalent to, saying that the mean width of T is at most the inf over all admissible sequences of the sum r goes from 1 to infinity of 2 to the r over 2 times the sup over x and t of the distance in L2 from x to tr. Okay. So I don't want to write down, I mean, yeah, I'm realizing that we are still, okay, so I don't want to write exactly y down, but let me kind of talk you through this. So for any given r, the thing that matters is this, right? The sup of the distance from any x to tr. So if you're trying to choose a tr to optimize this, what should you do? What you should do is the following. Notice that you're given a budget. You can make TR whatever you want as long as you don't make it too big. Its size should not exceed 2 to the 2 to the r. So if you're trying to minimize the sup over x and t of the distance to TR, basically what you're trying to do is, given this budget of how big the set can be, make it the best epsilon net it can be under that size constraint. Like make epsilon as small as possible. Okay. So then you should think of that sup of the distance as being epsilon. It's the epsilon such that TR is an epsilon net. So that thing is epsilon. And what is 2 to the r over 2? 2 to the r over 2 is just square root log the size of TR. Right? So this looks a lot like the sum over a sequence of nets, the epsilon of that net times square root log the size of the net. That looks a whole lot like Dudley. Right? And in fact, the reason that it really is Dudley in disguise is, if you think about it, like, okay, so let's say Dudley says I'm going to take a 1 net, then a half net, then a quarter net, then an eighth net, etc. I'm going to make epsilon be 1 over 2 to the s. Okay. So initially, in this thing that I wrote down, initially our budget for the size of TR is 1, because T0 is size 1. And we can start to slowly grow TR. Okay. So for a while, the quality of the net, the epsilon that it achieves, is between 1 and a half, right? So for some prefix of the r's, epsilon is basically between 1 and a half. So let's say that, so it's roughly 1. Meanwhile, what's happening to 2 to the r over 2? It's a geometric series, right? We have 2 to the 1 over 2 plus 2 to the 2 over, we have basically 2 to the 1 half is root 2. So we have root 2 to the 1 plus root 2 to the 2 plus root 2 cubed, etc. That's a geometric series with base root 2. So a geometric series here is dominated by its last term. So for a while, we have epsilon being 1 times this geometric series dominated by its last term. Okay. All right, let's write it like this. We basically something like at most like a half times this geometric series. So it's dominated by its last term. So what we have is kind of root log the size of a 1/2 net times a half. And then the quality of our net for a while is between a half and a quarter. And then we have another geometric series that starts from there, right? And then it's dominated by its last term until finally it hits a quarter, it goes under a quarter. And then we can bound that part of the sum by a quarter times square root log the size of a quarter net. So we can basically break up the sum, this infinite sum, we can break it up into blocks based on when the sup decreases by powers of 2. And then each block itself is a geometric sum dominated by its last term, which corresponds to one term in the Dudley sum. Okay, so what I claim is that this summation here, up to some constant factor, gives you the same exact thing as the Dudley sum, as long as you choose the TR optimally to be the best nets they can be. Does that make sense? I don't know, I'm hearing crickets, so at least type it. I can see the chat, so if it makes sense, at least say so in the chat. And while you do that, I'm going to try to find my iPad pen, because I seem to have put it somewhere, and I have no idea where I put my pen pencil, which was just in my hand a moment ago. This is so weird. Oh, there it is. Okay, so no one said anything, so I'm assuming that you all get it. Yeah?
Oh, I was gonna say, yeah, I think it must make sense.
Okay, good. So the magic.
Yeah, I have a question.
Oh, yeah.
Why do we need the TRs to be bounded by 2 to the 2 to the R rather than just 2 to the R? Or why is 2 to the R not enough?
Maybe it's just convention. There's no.
Oh, okay.
Well, okay. It's going to matter for the next thing I say.
Okay, yeah.
Yeah, so the next thing I'm going to say is that there's a theorem by Fernique, kind of recast by Talleyrand. That says actually WT is at most the inf over admissible TRs of the sup over x and t of the sum r goes from 1 to infinity of 2 to the r over 2 times the distance in L2 from x to tr. We took the sup, it's the same exact thing, but we took the sup outside the sum instead of inside. Taking the sup outside the sum can potentially make something smaller, right? It makes the whole thing smaller. But the magic of Fernique and Talleyrand is that even if you pull the sup outside, this is still a correct upper bound. The proof that this is a correct upper bound is not the same as the proof on the last whiteboard. You need to do a more custom proof, but it's doable, and I'm not going to do it today. Maybe I'll put it in the notes, or maybe I'll link to something for further reading if you'd like. Okay, and then the theorem, another theorem, which is called the majorizing measures theorem. And this is the magic, is that for all t, the mean width of t is at least that inf. So not only is this an upper bound, but it's also a lower bound up to a constant factor. And also, let me just give a definition. This thing here is just defined to be, I'll use notation. This is called gamma 2, the gamma 2 of t with respect to the L2 one. So the theorem is that for all t, the mean width of t is equal to, up to a constant factor, gamma 2 of t with respect to L2. Okay. And you can. Maybe I'll leave it as an exercise. You can read about it. If you then tried to optimize this thing for the L1 ball, you would get the right answer. I mean, you have to get the right answer because that's what the theorem says. But in fact, you can do it and you'll get the right answer. Okay, so now let me show you. So we saw already that the union bound alone was already enough to get the right answer for JL, to imply JL. Let me show you now that Dudley's inequality is already enough to get the right answer for subspace embeddings, and it's also enough to get the right answer for RIP. So Dudley implies OSEs, and also Dudley plus the Gordon. So you do Gordon, and then you apply Dudley to Gordon. OSEs and RIP. So let's do OSEs, oblivious subspace embeddings. So E is a d-dimensional subspace, and T is equal to E intersect Sn minus 1. So what is WT? It is equal to the expectation of, well, okay. To be fair, you don't really even need to do Dudley here, actually. So let's write it down. This is expectation over G of the sup over X and T of G dot X. Okay. So remember now, the Gaussian distribution is rotationally invariant. So if you're taking, so you might as well rotate the whole picture and just pretend that the subspace is actually the span of of E1 up to ED, right? Like without loss of generality, E is just equal to the span of E1 up to ED. To be more formal about it, I could write this as, so let's say G dot X. Oops, I could write this as follows, right? So like I guess what I'm saying, so Q transpose Q is equal to the identity, right? This is a rotation matrix. So what I'm saying is like, let Q be a rotation matrix that rotates the subspace to be the subspace, which is the span of E1 up to ED. Okay. Then QG, basically QG is equal in distribution to just G. Because if you take a Gaussian and you rotate it, you just get back a Gaussian. So without loss of generality, I can just rotate however I want. So I can rotate so that the vectors are just in the span of E1 up to ED. And then now this is basically equal to the expectation over G of the sup over X in the d-dimensional L2 ball of unit norm of G dot X. But again, L2 is its own dual norm. So this is just the expectation of G2, which is at most the expectation of G2 squared square root, which is root D. So, bam, we're done. Okay. So the Gaussian mean width of a d-dimensional subspace intersected with the unit sphere is at most root D. So the Gaussian mean width squared is D. So you get D over epsilon squared, which is exactly what you got in the P set. So, or via Dudley, let's say, let's prove the same thing via Dudley. WT is at most the integral from 0 to infinity of square root log of the covering number of TL2U du. So first of all, I really only have to integrate to 1 because like once U is bigger than 1, I can just make the net be a single point because everything in the unit ball is within one of the point 0. And then log of 1 is 0. So everything I'm integrating beyond U equals 1 is just 0 anyway. So let's just I'm only going to integrate up to U being 1. And then now we saw this before. The d-dimensional ball has in L2 has epsilon covering number of L2 of something like 1 over epsilon to the dimension. So this is at most integral from 0 to 1 of root log of something like some constant over epsilon to the dimension. Epsilon is U. To U, which is equal to root D times the integral from 0 to 1 of root log some constant over U du. And you can prove that this thing converges. So this is some constant. So this is O over D. Does that make sense? Okay. And it's honestly very similar for RIP. So for RIP, again, if you say if I want to bound the covering number, I mean the observation for RIP is that I'm trying to preserve n choose k different subspaces, one for each choice of which k coordinates define the sparsity pattern. So the covering number is going to be something like n choose k times c over u to the k. So for RIP, I'll just write it. For RIP, we'll get that WT is at most the integral from 0 to 1 square root log of n choose k times c over u to the k du. And again, just because log of AB is equal to log A plus log B, what you're going to end up getting is something like this is going to be at, at most root log of n choose k plus root k. And then, and this is basically the dominant term. So this is going to be at most root of k times log of en over k or something. Okay. So enough of all that. Let's now prove Gordon's theorem. But before I prove Gordon's theorem, does anyone have questions? Okay. So we'll prove something that's due to KMR. So Kramer, Mendelssohn, and Rahout, 2014. They say let script A be a set of matrices. Also, sigma 1 up to sigma n are IID plus minus 1. Then, if you look at the expectation over sigma of the sup over all matrices A in script A of A sigma L2 norm squared minus the expectation of A sigma L2 norm squared. This is at most, bear with me for a second. Gamma 2 squared of script A with respect to the operator norm plus gamma 2 of script A with respect to the operator norm times the Frobenius radius of script A plus the Frobenius radius of script A times the operator norm radius. Okay, so first I'm going to show you, it's going to be easy. I'm going to show you that this theorem implies Gordon's theorem, at least if the matrix pi has plus minus 1 entries as opposed to Gaussian entries. Okay, and then once we see that, then I'll prove KMR. Okay. So just remember what gamma 2 means. Gamma 2 means this, right? So what I'm saying now is we're not taking gamma 2 of a set of vectors with respect to L2. Instead, we're taking gamma 2 of a set of matrices with respect to the operator norm. So this is going to be the operator norm. And the TRs are actually going to be like subsets of script A. So the TRs for us are actually going to be subsets of matrices. Okay. So now the claim, or the observation, is that and actually KMR proved this not just for plus minus 1s, they proved it for any sub-Gaussian distribution. So in particular, the KMR theorem holds for Gaussians too. But I'm going to prove it today just for plus minus 1s because it makes things slightly easier. The observation is that KMR implies what I'll call the Rademacher-Gordon. KMR plus majorizing measures. Because what we're actually going to show is that as long as the number of rows of pi is at least gamma 2 squared over epsilon squared, you'll preserve the vectors. But then majorizing measures says that gamma 2 and mean width are the same thing up to a constant. So that means that you can set the number of rows to be the Gaussian mean width squared. So this KMR that I wrote up here implies the Rademacher version of Gordon, where the matrix has Rademachers as entries as opposed to Gaussians. So why is this the case? it's something that we've seen before. Okay? Which is, I can define for a vector x in Rn, I can define, actually, let me not write the dimension here. It's not really relevant. I can define Ax as being, this matrix 1 over let's say for vector x in Rn, also pi in Rn by n, pi ij is equal to like sigma ij over root m. I can define a matrix A sub x, which is 1 over root m times x transpose, x transpose, x transpose, where everything else is 0. So the dimensionality here is the number of columns is mn, and the number of rows is m. Okay. Now, if I look at, notice that if I look at the operator norm of AX, oh yeah, so actually what I wanted to say is just this. Pi x L2 norm squared is the same thing as AX sigma L2 norm squared. Where actually now sigma is a really big vector. It's like mn dimensional. You basically concatenate the rows of pi. So here you have sigma 1, 1 up to sigma 1n, then you have sigma 2, 1 up to sigma 2n, all the way down to sigma m1 up to sigma mn. Right, so I claim that this is true. Right? And we're trying to understand the sup of pi xl2 norm squared minus xl2 norm squared, which is 1. So this is saying that it's equivalent to understand, this thing. We're now, script A is basically the set of all A sub x's such that x is in T. Does that make sense? And KMR gives us something on the right-hand side that depends on Frobenius norms and operator norms. Well, let's try to understand that. Okay. Gamma 2 only depends on distances under the norm under consideration. So what is the distance? What is the operator norm distance between AX and AY? Well, if you look at the operator norm of AX minus the operator norm of AY, the first observation is that AX minus AY is just A sub x minus y. So this is equal to the operator norm of A sub x minus y. And that's equal to the L2 norm of x minus y over root m, because there's a division by root m over here. Does this look familiar? I think we reasoned about these A sub x's before when we were proving JL and sparse JL using the Hansen-Wright inequality. I know it's been maybe a month or 6 weeks now, but is this looking familiar to people?
Somewhat.
Yeah, probably.
So, I mean, this implies that gamma 2 of script A with respect to the operator norm is equal to gamma 2 of T with respect to the L2 norm over root m. And what's the largest? So df of script A is like the max, it's the sup over all A in script A of the Frobenius norm of A. But this is just equal to the sup over all x and t of the Frobenius norm of AX, right? And this is 1. You can just do a calculation. That's 1. And similarly, dL2 to L2 of script A, you can also prove is just 1. So KMR implies that, the expectation over pi of the sup over x and t of pi x L2 norm squared minus 1 is equal to the expectation over sigma of the sup over a and script a of a sigma L2 norm squared minus the expectation of a sigma L2 norm squared, which is at most what we know, gamma 2 squared of script a operator norm plus whatever. But if you convert that to what it means in terms of t, it's gamma 2 squared of t with respect to L2 over m plus gamma 2 of t with respect to L2 over root m plus, I have to say this should be 1 over, I think this should be, yeah, this should be 1, and this should be 1 over root m, sorry, plus 1 over root m. So this is at most epsilon as long as m is at least gamma 2 squared of t L2 plus 1 over epsilon squared. But we know that gamma 2 squared and width squared are the same up to a constant. That's the majorizing measures theorem. So this is the same thing as the width squared of t plus 1 over epsilon squared. So really the only thing that's not obvious in all of this is like, why is this true? Right? Like, how do you actually prove the KMR theorem that you can bound that thing by the gamma 2 in terms of gamma 2 with respect to operator norm and blah, blah, blah. Like,
Well, you're saying that entire right-hand side is upper bounded by epsilon, or just the first term?
You want the entire right-hand side to be bounded by
Yeah.
epsilon.
Yeah. Okay.
So if you set m to be gamma 2 squared over epsilon squared, then the first term is going to be epsilon squared. The second term is going to be epsilon.
Right. Yeah.
And the last term is also going to be, because you have a plus 1 there, so the last term is also going to be less than epsilon. So the whole thing is going to be O of epsilon.
Yeah.
Does that sound reasonable?
Yeah. Yeah.
Any questions before we try to prove KMR? I'm not 100% confident that we'll be able to finish the proof of KMR in 15 minutes, but I think we'll at least be able to like almost prove it and get all the main ideas across, and then whatever's left, I'll just put in the notes. Okay, so are people psyched? Yeah?
Yes.
So let's prove it. So notation. A has columns A1, A2, up to A whatever the dimension is. That's one thing. And then the other thing I want to say is, like, if TR is admissible sequence, then pi r A is defined to be the closest point to A in TR under operator norm. And delta R of A is defined to be pi R A minus pi R minus 1 of A. Okay? So that's it for notation. So now the first thing, I'm going to define the error to be the thing we're trying to bound. The error is the expectation over sigma, the sup over all A in script A of A sigma L2 norm squared minus the expectation of A sigma L2 norm squared. So I can write this as the expectation over sigma of the sup over A in script A of, like, remember that A sigma is equal to the sum of sigma I AI, right? This is what I wrote in the top right here. Oh, I just saw your chat, Alex. I'm glad that you're excited. Okay, so this is equal to basically the dot product of the sum of sigma I AI with itself minus the expectation. Okay. So notice that, like, basically, if when you have the diagonal terms in the dot product, you're going to have sigma I squared. So, okay, let me just write it like this. This is equal to the expectation over sigma of the sup of sum over all ij of sigma I, sigma j, dot product of ai dot aj, kind of minus that expectation over there. And I claim that the diagonal terms just cancel exactly with the expectation. The diagonal terms are the expectation. The off-diagonal terms have expectation 0. The diagonal term, sigma I squared, is 1. Okay, so they stay. So this is equal to expectation over sigma of the sup of the sum over I not equal to j of sigma I, sigma j, ai, aj. And so this is already in the notes in the probability review section. I'm not going to spend time proving it, especially since I don't have a lot of time. But there is a magic trick called decoupling that says this is at most 4 times the expectation over sigma n sigma prime of the sup over a of the sum I not equal to over the sum of I all ij, including the diagonal, of sigma I sigma j prime ai aj. So now we have like 2n random signs. Sigma 1 up to sigma n, sigma 1 prime up to sigma n prime. These are 2n plus minus 1s. They're all independent of each other. Okay. And then this is equal to 4 times the expectation over sigma sigma prime of the sup over a of a sigma dot a sigma prime, basically. Okay. So let's just remember now where we are. We've shown that E is at most up to a constant, which the constant is 4. The expectation over sigma n sigma prime of the sup over a and script a of a sigma dot with a sigma prime. Okay. Now a little bit of a magic trick. I claim that for any fixed a sigma dot a sigma prime is equal to. So remember now, I can write a as like pi 0a plus the sum r goes from 1 to infinity of delta ra. This is that same telescoping sum thing I did before when I was proving Dudley's inequality. Okay. And you can prove that this thing is equal to pi 0a sigma dotted with pi 0a sigma plus the sum r goes from 1 to infinity, okay, of delta ra sigma pi r minus 1a sigma prime plus the sum r goes from 1 to infinity of delta ra, or actually I'll write pi ra. Dotted with delta r. Okay, so that looks like a mouthful, but let's just think about what's happening. So first you start off, let's try to again expand out these sums like one term at a time. So first you have first you have like pi 0a dot pi 0a. Then when you add in the next terms from r equals 1, remember now delta r means pi r minus 1. So you basically get 2 terms from the first sum and 2 terms from the next sum, if you expand out delta r as the difference of 2 things. So you get 4 more terms. You get pi r dot pi r minus 1 plus or minus pi r minus 1 dot pi r minus 1. So right, so this is going to give you something like, let me like take a little shorthand. This is going to look something like pi r dot pi r minus 1 minus pi r minus 1 dot with pi r minus 1. But like this is going to cancel the previous summand, right? Remember we had pi 0 dot pi 0. So pi r minus, now when r is 1, pi r minus 1 is pi 0 dot pi 0. So it's going to cancel out with the previous thing. And then when you expand out this thing, you're going to get pi r dot pi r minus pi r dot pi r minus 1. So then this minus pi r minus, this minus here is going to cancel with this thing. So the only thing that remains, that survives, is this. So first you had pi 0 dot pi 0. Then when you expand things out for r equals 1, everything cancels except for pi 1 dot pi 1. Then when you expand out, when you add in the next summand, you get pi 2 dot pi 2, etc. And then eventually, because script A is finite, again, without loss of generality, script A is finite. Because script A is finite, eventually all the delta r's are 0, which means that you're going to end up with, like, this is just some massive telescoping sum. That's a fancy way of writing a sigma dot a sigma prime. Okay. And now let me make some definitions. I'm going to call this, I'm going to call XRA. And this I'm going to call YRA. So this implies that E is at most pi 0a dot pi to sigma, pi 0a sigma prime, plus the sum r goes from 1 to infinity of XRA. There should be a soup, sorry. So there should be soups. Let me erase all this. Sorry. Let's put the soups back. Is at most the expectation of the soup over A of A sigma, pi 0. Pi 0a sigma, pi 0a sigma prime, plus the expectation over sigma prime of the soup over A of the sum over R of XRA, plus the expectation of the soup of the sum over R of YRA. And Y and X look quite similar to each other. So like the same way that you analyze this is going to work to also analyze this. So we'll only have to focus on one of them. The other one is the same. So let's do that. But first, let's look at this thing. So again, remember that the definition of a miscible sequence, T0 has size 1. So really, there's only one matrix pi 0a. Let's just call it, every single A has the same pi 0a. Let's just call it A0. So this is just equal to the expectation over sigma and sigma prime of actually, let me put, yeah, so I wanted to write A0, oops, A0 sigma, go with A0 sigma prime. And then I want to write, this is at most, so this is equal to expectation of like sigma transpose A transpose A sigma prime. A0, this is 0. Which actually is interesting because that's 0, but maybe we could have gotten rid of it. If you had, I don't know if I lost an absolute value anywhere. If I did, oh yeah, I did lose an absolute value. Remember now, there's an absolute value around all of this. So I should have kept my absolute value. So really there's an absolute value here too. So this is at most the expectation of that thing squared, square root, which turns out to be the Frobenius norm of A0 transpose A0, which is at most the operator norm of A0 times the Frobenius norm of A0. So this is at most D L2 to L2 of A the largest operator norm of anything in A times the largest forbidding norm of anything in A. Okay, so we bounded the first term. Okay, so how do we bound the next term? So now we have to just focus on this thing. So expectation of sigma dot sigma prime of the sup over A in script A of the sum R goes from 1 to infinity of XRA. And just a reminder of what XRA is. XRA is equal to delta RA applied to sigma dotted with pi R minus 1. A applied to, applied to sigma prime. Okay. So this thing is equal to the expectation over sigma prime of, now again, right, the expectation of a non-negative random variable, like the expectation of z is equal to the probability, is equal to the integral of the probability that z is bigger than u du. Right? This follows by integration. This follows from integration by parts. So this is equal to the integral from 0 to infinity of the probability over sigma that the sup over A in script A of the sum R goes from 1 to infinity of XRA is bigger than U du. And now I can do a change of variables, and I'm going to do sort of a magic change of variables that I'm doing it just because it makes the proof work out. But I admit that it is a little bit of magic. So this is equal to now the expectation over sigma prime of the following thing. The sup over A in script A of A sigma prime, okay, times the sup over A in script A of the sum R goes from 1 to infinity of 2 to the R over 2 times the norm of delta RA, the operator norm, times the integral of from 0 to infinity of the probability over sigma of that the sup over A in script A of the sum of R goes from 1 to infinity of XRA is bigger than T times the sup over A in script A of the sum R goes from 1 to infinity of 2 to the R over 2 delta RA times the sup over A of A sigma prime. Okay, that looks like a mouthful. DT. So all I did, like if you just call this thing beta, all I did was a U substitution. I just said that I just did the substitution U is equal to T times beta, which implies that du is equal to dt times beta. Okay. And now, okay, we're almost out of time. So I think, but we're almost done with this proof, even though it looks like a mouthful. So here's kind of the idea now. We're going to end up using Khinchin's inequality and a giant union bound. So we're going to say, look, so this integral, I can write as like the integral from 0 to 3 of that probability plus the integral from 3 to infinity of that probability. This is at most 3. Okay. For this thing, I'm going to use the union bound. Okay. So what's the probability that there exists an R and that there exists an A in script A such that XRA is bigger than t 2 to the r over 2 times delta RA transpose times pi r minus 1a. Okay, so this again looks like a mouthful. But let's remember what XRA is. I wrote it up here at the top. I can write that as sigma dotted with delta RA transpose pi r minus 1 a sigma prime. Does that make sense? Like if I write b sigma dot b prime sigma prime, that's the same thing as sigma transpose b prime sigma prime, which is the same thing as sigma dotted with b transpose b prime sigma prime. So I can move this matrix to the other side by transposing it, right? And then I can do Khinchin's inequality. Khinchin's inequality says if you take a sign vector and you dot it with some other fixed vector, what's the probability that you're bigger than lambda times its L2 norm? It's at most e to the minus lambda squared. So that's what I'm doing here. I'm saying, look, that thing on the right-hand side has norm equal to this. So what's the probability that I'm more than t times 2 to the r over 2 times that norm? It's at most something like e to the minus t squared 2 to the r over 2 times and I should really say I'm going to union bound over all r, because I said what's the probability that there exists r? What's the probability that there exists an r where this is true? What's the probability that there exists an a? So if you fix an r and you fix an a, this is your tail bound. This is just Khinchin. But if you want to union bound over all r, you're going to sum this thing over all r. And then if you're going to union bound over all a, well, how many possibilities are there for delta r of a and pi r of a? At most, something like the size of tr times the size of tr minus 1, which is something like 2 to the r plus 1. So if you look at what's in that sum, I know, again, this is a lot of math here, but you have 2 to the r times e to the minus t squared 2 to the r. Okay? Now, e to the minus t squared, 2 to the minus, imagine the base was not e, but the base was 2. I can do a change of base and lose a constant in the exponent. So I have 2 to the r times 2 to the minus t squared 2 to the r. If t is a big enough constant, like if t is at least 3, then 2 to the minus 8 times 2 to the r is way smaller than 2 to the 2 to the r, because there's an 8 there in the exponent. So this sum, it converges. Okay, so that's the point. The point now is this part here, this integral here, I can write as being at most the sum over all r from, reverse the order of the sum in the integral, r from 1 to infinity, of the integral from 3 to infinity of e to the minus t squared 2 to the r over 2 times 2 to the r plus 1 dt. And this whole thing, I promise you, converges. It converges to some constant. It's bounded. So this whole mess of a thing here, all this stuff over here is basically a constant. The only thing that survives is this part. Beta survives. The rest is a constant. So what we have then is that this implies that the expectation of the sup of the sum of XRA is at most up to a constant. The expectation, this is the expectation over sigma prime. actually over sigma prime of the sup over A and script A of A sigma prime times the other thing, which again, I think we're way over time. The other thing is basically gamma 2. It's bounded by gamma 2 up to a constant. Gamma 2 of script A with respect to the operator norm. Okay. So this magic of doing a change of variables in the integral basically gives you a gamma 2. Like this thing here is bounded by gamma 2. And I don't have time. I'm out of time. I'll include the details of that in the notes, but it's a simple triangle inequality to say that this thing is bounded by gamma 2. And then if you just keep going, you can wrap this up and get the bound that I showed you. So I'm afraid I'm more than 5 minutes over time, so I'm going to stop here. And if you want to see the details of these calculations, at least I hope I at least gave you a flavor of the calculations and I showed you once you have it how it implies Gordon's theorem. But I'll put the details in the notes. And I think that's it for lecture. And are there any questions?